Alright, I hope everyone's signed in. Okay. Why is this thing down here? How do I get rid of it? Alright, everyone sign in. Okay, cool. Alright, so, hello everyone. My name is Charles. I'm a junior studying business and computer science, and I'm part of MIC, and I serve as treasurer. Today we'll be talking about convolutional neural networks. And before we dive in, who here went to the neural networks workshop? Great. So essentially, I'll dive into this a bit more later, but a convolutional neural network is essentially what it sounds like. We have neural networks, right? And then we're going to put a bunch of convolutional layers in front of them. Now it's a convolutional neural network. And this workshop, the presentation itself will be a bit shorter than usual, but we have this Colab notebook, Jupyter notebook for you to mess around with afterwards. That might take a bit. Some people might get stuck. We have answers if you need them, but try not to look at them. And we'll have a link to that at the end. So let's get right into it. Also, if I'm going too fast or anything, let me know. Just like raise your hand or something. I tend to rush. Okay, so we'll start off with compositional data. So a convolutional neural network takes in compositional data as its input at the very beginning of all the convolutional layers. And so you might be wondering, what is compositional data? And compositional data is what it says up here. So essentially, if you want to think about it, if we took this Facebook profile and wanted to represent it as a piece of data, every single data point within that piece of data would be things like, let's say, your number of friends, percentage of likes via posts, stuff like that. And essentially, those data points together represent this entire entity, right? That's what a piece of compositional data is, and that's what a convolutional neural network will take it as input. So we have a couple more examples here. For example, a table, maybe some pieces of data that pertain to it are like what it's made of, how polished it is, number of likes, stuff like that. And why do you care, right? Well, I told you already earlier, you use it as input of the convolutional neural network, but also it's used just widely in machine learning as well, as opposed to deep learning. And so, specifically, since we're talking about convolutional neural networks specifically, we're going to use it to aid in image classification. So, for those of you who don't know, images on computers are represented, especially colored ones, are represented as a bunch of RGB matrices overlapped on each other. So, let's say you have this 5 by 10 pixel image of a bird. Well, that bird, if it's colored, would be represented by 3 RGB matrices, a red matrix, a blue matrix, a green matrix, and a blue matrix. And all of those would also be 5 by 10. And that's how they're represented. And so, if we want to kind of apply compositional data to this, we can think of it as looking for features, or specific pieces of color, I guess, in these various RGB matrices. And those, if you have enough of these pieces of color that would pertain to a bird, then the probability is high that the image is actually a bird, because those pieces of color kind of sum together and represent this entire entity of a bird. Did everyone get that? Was that clear? Okay, cool. Moving on. And so how do we actually identify these features, and then once we've identified them, use them to determine whether or not the image is a bird? This is where convolutions come in. And so convolutions, essentially, you can think of it as this way. So let's say we have a falling ball, like right here. So this ball falls, lands here, right? And then there's a probability that it travels distance A to this point over here. Once it's at this point, there's also a probability of it traveling distance B and landing at this point over here. So now this ball is A plus B distance away from the original point where it fell down. And essentially the probability of the event A occurring as well as the event B occurring when you apply it into a convolution is the probability of the event A plus B occurring. And so if we think about about it in terms of compositional data as well as convolutional layers, if you have an image that's a bird, right? Let's say a couple of features that we're looking for in a bird are like an orange beak and like a feathery texture or something like that, right? So if a random image that's input has a feathery texture feature in it, there's a slight probability, slight chance that it would be a bird, right? But if it also has an orange beak feature, then the probability goes up because it has two features that are specific to a bird. And as we keep adding on more features, the convolutional layer will kind of keep increasing the probability that this image is actually a bird. And so this is just another way to kind of look at the falling ball analogy. So let's say the ball falls here, right? And then it kind of lands there, somewhere around there. It's again just the probability of one outcome happening after another. In the context of image classification, the probability of one feature and another feature leading to the actual input being a specific animal or class or whatever you're trying to classify it as. And finally, we're going to, well, essentially, the original point, the point of like this convolutional layer is you're going to want to pass a bunch of input into it. And then at the end, in the very first like training epoch, you're probably not going to be able to classify that many things. So we're going to want to go back and kind of readjust these convolutional layers. And that's where the inverse function comes in. And we're not going to go into the mathematical basis of the inverse function, but essentially you just think of it as you have these outputs, right? Now, using the inverse function that created the output, we can find some possibilities of where the output came from. So it's very simple. So let's say you input an image that's a bird, and then it classifies it as a fish. But one of the possibilities from the inverse function says that it could have been an input image of a bird. And so you do that and you kind of play around with that too, or just use that to go back and try and optimize your convolutional layers. And so this brings us to actual convolutional neural networks. I'm not going to cover the neural networks part since it's already been covered, but again, as I mentioned before, convolutional neural network, it's a bunch of convolutional layers stacked in front of the neural network layers. Once we finish with the convolutions, we'll pass that output into your neural network layers, pass it through the neural network, go check out our slides on GitHub for that, and we'll get a couple of classifications as output, which we can use to determine what the image actually is. And convolutional neural networks aren't only for like image classification. It also, it can be used for image classification or like feature recognition, object recognition, essentially in the first point. It can also be used for self-driving cars, as well as learning some game. And we won't go into those other two because they get a bit more complex. But AlphaGo is pretty cool. It's a very complex game. Humans beat it with AI. I guess AI beat humans. And then Mario, same thing. There's a lot of stuff that you can do in Mario. You got to make sure that you win, and you can do that with convolutional neural networks. And so here's the actual structure. Yeah, okay, that's everything. So essentially you have your input, right? Let's say it's a car. You're going to pass it into the convolution, and we'll explain what's going on here in a bit. After this, we'll have a pooling layer, which we'll explain, we'll get to it. Maybe pass it into a couple other convolutional layers, a couple other pooling layers, etc., etc. And then finally, we have this very long matrix. So essentially, it's a 3D matrix. We have a lot of 2D matrices in there. We're going to flatten all that and pass it into our actual neural network, and that'll do the classification for us. And at the end, there's traditionally a softmax function in the convolutional neural network, and that's just because, well, I'll get into that at the last slide, but traditionally we use that. And so, first part, convolutional layer. What's actually going on in there? So essentially what's happening is you have this input image, right? Your input image is a bunch of matrices. They could be just a 2D matrix if it's like black and white, for example. Yes. And then, or it could be like colored, right? And it would be a 3D matrix, and it would have an RGB matrices corresponding to each color pixel. And so what the convolution is actually doing is the convolutions have certain features that you're looking for. So as going back to our original example of a bird, let's say a feature of an orange beak is this this square right here. We're looking for an orange beak with this square. It's represented by these ones. So we're going to take this kind of 3 by 3 matrix, which represents the filter or the feature that you're looking for, and we're going to iterate through the actual. Excuse me, I would cough this wall. And we're going to iterate through the input image. And so what we're going to do there is we're going to actually take the dot product of this filter as well as the input image, and that will compute the probability of that kind of part of the input image being an actual feature. And that way we can kind of go through the entire image, and we'll be able to find out whether or not that input image has this feature that we're looking for. The next slide has some more math. So yeah, here's like what's actually happening. Let's say again we have this 3 by 3 feature that we're looking for. We have this, what is this, 8 by 8 input image that we're going to go through with this 3 by 3. We're going to go through it. We're going to look at this thing. We're going to look at this thing, and then everything will be. We'll do a dot product and everything, and then map it to its appropriate pixel in the output map. And so the dot product's right here. So essentially, you can just think of it as we have 3 by 3 matrices, right? You might be thinking, why are we doing a dot product on 2 matrices? But we're going to flatten them into vectors and then do the dot product. And that's what's happening here. So 3 times -1 plus 0 times 0 plus 1 times 1, etc. And then we get this output that we're going to put into our output map. And we move along to continue filling out that output map. Any questions? Okay. No, we're smart. Okay, and then what we're going to do next, so if we go back actually, we're going to see that the output here is -3. But you might be like, what does -3 mean? It doesn't mean anything to you. And so that's why we're going to normalize it. So essentially what normalization is doing is it just takes your output from the dot product, so like back here. It'll take this output, and then it'll divide it by the max possible value. So like if it were actually a feature. And that'll give you a value between 0 and 1. And that'll also just tell you how likely that like kind of part of the input image is that feature that we're looking for. And so that's just what normalization is doing. So if you see here, if we kind of did the convolutional layer for this input with this filter, we're going to get this after normalizing it. And so you can see that like kind of along this, since we're looking for a kind of diagonal line here from left to right, these values, all the ones, show that, right here, show that those were actually full diagonal, like completely matched. So that's why they have a probability of 1. Questions? Okay. And so the last part of the convolutional layer that we can talk about, well actually there are a lot more parts, but the basics of it include a couple of hyperparameters. Who knows what a hyperparameter is?
It's just like parameters you can just like fine tune how you like train or like the actual structure of like your network.
Yeah, exactly. So it's like your parameters that you yourself will modify, as opposed to your weights, right? Which are called not your hyperparameters, your regular parameters. Your weights, your network will kind of train with the function that you make. So here are like 3 hyperparameters that you're going to kind of play around with in your convolution to try and optimize it. So the first thing is stride. So here, let's go back to another slide to kind of illustrate this. So we have this large input matrix, and we have the filters. So we check this 3 by 3 section, this 3 by 3 section, this 3 by 3 section, etc., right? And it produces this map right here. But doing this kind of overlaps, right? And sometimes with like by going 1 by 1, it's a lot less computationally efficient. So what stride is it just tells you how much you should move this filter every single time. So let's say you have a stride of 1. You would be doing exactly what we just did. Move along 1 column at a time slowly. But if we got a stride of 3, for example, we'd actually check this one, we check this one, we check this one, and there we go. Go. And that's more efficient, and then there are a couple other advantages to it. Another hyperparameter that you'll need to kind of mess around with for a convolutional layer is padding. So this is a very very even matrix, so you might not need any padding. But essentially what padding is it's just adding a bunch of zeros around the edge. Why might you do that? Well, if you had a 2x2 filter here, for example, and you did in a stride of 2, you go this, and then suddenly there's nothing here. There's only a single column left. So you're going to want to add an extra column with zeros there, so you can actually include these features in your final output map. And if you don't, you might run into some problems later on. You just want to make sure that you're ingesting all the information. And that's why you would use padding. One of the reasons why you use padding. And the last thing is depth. Depth is just the number of features that you're looking for. By the way, filters just look for features. Just clear that up. So depth is the number of filters you have. So essentially, how many features you're going to look for. And so let's say you had your bird, right? You're looking for 3 features. I don't know, like feathers, beak, and wings. Now you would have a depth of 3 because you're looking for 3 features, and you need 3 filters to look for those 3 features. Questions? Yeah. Okay. Cool. And now we get to the pooling layer. So we just talked about convolutions, and if you go back to the original thing over here, after convolutions, we have pooling. And let me just briefly go over ReLU since I kind of took that out. If you were at the Neural Networks workshop, ReLU is an activation function. Activation functions, they map linear data to nonlinear data. And then ReLU just takes the max of 0 or the actual input. So you don't want any negative numbers because, well, if you're normalizing it correctly, you don't want a negative probability. That's you want 0 to 1. Sorry. So after ReLU, we'll put everything into a pooling layer, and we have this mapping here. These aren't normalized, as you can see, but this is just for purposes of explaining the pooling layer. So the pooling layer, it takes your output map, so the thing on the right there, takes that, and then it'll again go through everything with a set size matrix. So for example here, it's a 2x2 matrix, and we go through this output map that's 4x4, and it's going to apply a function to every 2x2 chunk here. And output, so for example, a very popular is max, we want to apply the max function to 2x2 chunks. It'll just take this, find the max, put it in the output map here. Take this, find the max, output map. 3, 3, 4, 4. And that's what it's going to do. And the reason we want to do this, one reason, computational efficiency. Now, if we want to pass this final output map to a neural network, it's going to be a 1x4 vector as opposed to 1x16. It's a lot less computation. And then also, by dropping out some features that are supposedly less important, right? Since if these were normalizing in all the probabilities, this would be the highest probability. By dropping out these other features, we're going to be able to prevent overfitting. So let's say the network just started thinking that in order for this feature, which let's say it is a beak, because there's a 6 there, in order for this to be a beak, it also has to have these. That would be not true, right? We only want to pick the feature that's most important. That's why we're going to do like a max pooling function on it, for example, and pick out the most important feature there. Yeah, questions? Okay. All right, and then after max pooling, and then maybe a couple other convolutional layers, et cetera, we're going to have our final output map that we're going to want to pass into our neural network. And so before we do it, as many of you may know, neural network takes in a vector as input, right? So we're going to have to take our output map and flatten it. Excuse me. And so it'll take your output map, it'll flatten it in, pass it to the neural network. Again, with the neural network, you can play with the number of layers you want, and the number of classes you want to kind of output at the end. So for example, here, the final output layer has 10 nodes, pretend there's a dot there. Then you're going to be trying to classify your inputs into 1 of 10 classes. So yeah, you'll put your output map in there. It'll give you your classifications. If you want to learn more about what's actually happening there, refer to workshop number 2, neural networks. And so finally, after you pass everything to the neural network, you're going to actually, at the end, throw everything to a softmax function. And a softmax function is another activation function, maps linear to nonlinear data. Linear data to nonlinear data, sorry. And essentially what it's doing is it's going to take the highest probability value, which you already know is going to be the kind of class that you're classifying your input image as. So in this example, pass in this image, it classifies as an airplane. We already know that's an airplane, but we want to kind of get rid of these values right here because these aren't important since we already classified as this. And then if it's correct, right, we're going to not want to worry about these when we're classifying this. So the softmax function, it'll take everything, all the different classifications and the scorings for those, and it'll kind of increase the importance of the highest one, so the one that we actually scored it as, and decrease the importance of the others. Then when we scale it to actually probabilities, it'll come out to be this. Questions? Okay, was that too fast? All right, well, here's a link to a collab, collab Jupyter Notebook. So I believe this is view only, make your own copy.
If you have an input for like different sizes, I'll use patterns to have them create the convolutional network, if that makes sense.
What do you mean? What do you mean different sizes?
So let's say you have a bunch of different images and you're different dimensions, like pixel wise, you're trying to create a neural network. You use patterns that kind of fill in the small images and then just...
No, so padding's mostly used for when you're running the filters through your input image. We don't want it to accidentally skip an extra column. So like if the dimensions don't like kind of multiply into each other. So if you, for example, if you had a 3x3 filter and a 10x10 image and stride of 3, we look at the first three. We just look through kind of 9 columns, but the last one we can't really look at it, right? Unless we add a couple of zeros at the end. And so like if we didn't add zeros, we kind of move on to the next row.
So in practice, you have to process all the input information first, which was like size before setting 3, correct?
Yes.
Usually it's like fixed in both sides.
Say that again?
Usually I think it's like fixed in both sides.
Okay, got it.
Did everyone get this link? Who did not get the link yet? Yeah.
No, I just like, how does the mathematical concept of convolution connect to what we just did with like not running the matrices together?
It's a good question. Let's go back. Where is it? Oh, okay. Yeah, so, where is it? It's here. So, the convolution is like, where essentially if there are two features that are both present in an image, the probability of that image being the class that those features belongs to goes up, right? So when you're doing your various filters, and you have like, let's say 3 filters or 3 features that you're looking for, if the output map over here, this is only one feature, right? This is only one filter. It'll give you this regular 2D output map. But if you had 2 filters for example, looking for 2 features, like also looking for the diagonal from right to left.
Oh, I see. All right.
Yeah.
It's that way.
Anyone get the link? Oh yeah, I should put it back up. Who doesn't have the link? Okay. Here's the link. Yeah. Okay, cool. Also, before I X out and kind of walk you all through the notebook, thanks to our sponsors. Yeah. And then here's some references. And if you want to read like research papers or stuff, be my guest. Okay, so let me drag this over. Cool. Okay, cool. I can't really present this, but essentially now I'll be walking around helping y'all, but try to implement your own feed-forward convolutional layer, and then implement the softmax function. The first one should be a lot harder, you can ask the other MIC people, some of them. But yeah, and there's some function parameters here for you to look at. So just to clear things up a bit, you might be wondering why your input is four-dimensional, and that's because the height and the width, right? Those represent the actual size of your matrix. So let's say it were just black and white, right? It would just be a single matrix. It would be, it would just be a single matrix. It would be, I don't know, like 5 by 10, right? Number of image channels represents like the number of colors that are going in. So if you had a colored picture, that colored picture would have 3 image channels because it has the red matrix, it has the green matrix, as well as the blue matrix. And then D is the number of inputs, so how many images you're actually putting in. So that's why that's 4D, just one single input. And then your weights, so NF, number of filters in your filter map. So how many features you're looking for. C is the number of channels, so going back here, how many colors there are essentially, if you want to think of it that way. Height of your filters, width of your filters. So when I was looking for like maybe like a 3 by 3 feature and a 10 by 10 into a matrix, your height and width would be 3 because that's the size of the feature that you're looking for. And then you also have your bias. That's there to kind of make sure things like fit correctly. Like if you were to like, I don't know, graph it out, what if it were like missing? It would just like right below the actual fit, but it was a correct curve. You would just want to add a bias, like kind of y-intercept to move it up one. Stride is how big the step you want your filters to take. So we covered this a bit. It's like if you have a 3 by 3 matrix that you're like with your filter and then 10 by 10, how big a step you want it to take. Padding, how many zeros you want along the edge of your matrix. And those are both hyperparameters, right? So that's why you're passing into the function. It's up to you to kind of tune that and make sure it works out well. And then the output itself, so first of all, there should be an output for every input, right? So that's why, we go back up. Yeah, there should be, you have, I don't know, D number of inputs, right? So your output should also have D number of outputs. NF is the number of filters, and this is because since we're looking for, like what the question he asked earlier, if you have 2 features, the output map will be 3-dimensional and it'll have 2 matrices stacked on each other. And that's what the output should look like, since we're looking for those 2 features. H, the result of your filter, so like the output map itself, it should match your input dimensions. Same thing for weight. So, yeah. And the cache is just there. Good practice for it to be there. It's not like hard to code. And so here, essentially, I've given you just a couple of pieces of code here to extract all the parameters from the input. And each block that's separated by a new line should be a single line of code. And so essentially you'll be writing 5 lines of code here. And there are a couple of hints here to use some functions from NumPy. And yes. And then down here, softmax function. This should be fairly straightforward. And then if you need help, I'll walk around. brief interjection. It just brought to my attention that this function right here isn't actually built into NumPy. It's based on implementation. Let me add the link to the actual function there. Oh, that was the link. Here, I'll just do this instead. Where's my mouse? There you are. Okay, there we go. So essentially what this does is, if you read the comment here, it'll take your input x, and then it'll kind of convert it to a bunch of vectors, and then as well as the convolution that the filter size that you're looking for. Well, if you just multiply these together and multiply this together, you get dimensions. And the reason for that is just it makes this entire input a bit easier to process. So you'll get a bunch of essentially 9. You're going to get a bunch of 1 by 9 column vectors, 500 to be exact. And since when you're doing the filter on when you're mapping the filter onto the actual input, you're doing the dot product of the two. Doing the dot product on 1 by 9 vectors is a bit easier, and it's essentially what it's doing.